So more on the series parallel. Let's look at this example here. We've got a parallel feeding into a series, and it becomes a parallel. So first we find the current in I2 because the problem asks us to find the current in R4, which is this wayward resistor way out here, if the source voltage applied is 50. So once you know this current, then use the current divider formula to find I4 and the current through R4. So notice that there are two main branches in the circuit. The leftmost branch consists only of R1. The rightmost branch has R2 in series with a parallel combination R3 and R4. The voltage across both of these main branches is the same and equal to 5 volts. Okay, calculate the equivalent resistance, resistor R2 plus the parallel 3 and 4 of the most right branch, then apply Ohm's law. I2 is the total current through the main branch. Okay, so that's up here on R2. So if we look at this series parallel combination here on the far right, we can see that R2 plus 3 in parallel with 4 then is equal to R2 plus the product over the sum, which gives us 330 plus, again, the product over the sum, and we get 538 ohms. So that's the entire equivalent resistance on the far right side. So the current I2 then is equal to the source voltage and R2 plus the parallel combination R3 plus R4. Okay, so we have 5 volts divided by 538 ohms gives us 9.3 milliamps. Okay, so that's over here. Use the two resistor current divider formula then to calculate I4 right there. So I4 is equal to R3, the opposite resistor, divided by the sum R3 plus R4 times I2. So that gives us 330 ohms over 890 ohms, or 9.3 times 9.3 milliamps, or 3.45 milliamps. So that's our current here, I4. Using the voltage divider formula, Kirchhoff's voltage law, Ohm's law, or any combinations, find the current in any branch of series parallel. So in this case, we've got, again, a fairly simple circuit here. Find the voltage V1 across R1. So if we were to put a meter here across R1, we could measure V1. All right, so note that R1, R2, and R3 are in parallel in this circuit. So R2 and R3 right there are in parallel. Both have the same 560 ohm value. Since they are equal in value, their equivalent resistance from node A to ground then is 280 ohms. In the equivalent circuit shown here, R1 with the equivalent RA 280 ohms, the total circuit resistance is seen from the source as a series circuit, the sum of R1 and R sub A, which gives us 430 ohms. Use the voltage divider rule now to find the voltage across the parallel combination of this figure 721. So there's the parallel combination. All right, so between node A and ground. So there's node A, there's ground. So V sub A is equal to resistor A divided by the total times the voltage at the source. Okay, so we've got 280 ohms, 430 ohms for RA and R total times 80 volts gives us 52.1 volts. Now we use Kirchhoff's voltage law to find V1. So now it's just a matter of using the sums and differences. So the source is equal to V1 plus VA, or V1 is equal to the source minus VA. So 80 volts minus 52.1 volts gives us 27.9 volts is the voltage drop across R1. Okay, so this one becomes a little more sophisticated. When we come back, we'll tackle example 711.